Three missions: Apollo 11, Apollo 13, and Artemis 2. Three trajectories to the Moon. At first glance, they look similar. But each path reveals a different strategy and a different era. Apollo 11 and 13 begins in low Earth orbit, followed by the same outward injection, a stable parking orbit, preparing for the precise moment to depart. Now, Trans-Lunar Injection. A single powerful burn stretches the orbit into a long ellipse, escaping Earth's gravity well. If left untouched, the spacecraft would loop around the Moon and come back to Earth automatically. But Apollo 11 does not simply pass by. A braking burn captures it into lunar orbit. Here, the mission transitions from transit to landing operations. But things had to change for Apollo 13. After the onboard explosion, the mission commits to the free return path. No capture burn, no descent. The Moon's gravity bends the trajectory sharply, turning the spacecraft around. This is passive navigation at its most critical. The path itself becomes the rescue. Now, as you may have noticed for Artemis 2, immediately the difference is clear. Instead of a short parking orbit, the spacecraft performs extended Earth orbits. These high, stretched orbits build energy gradually, a modern approach that increases flexibility and safety margins. Only after this build-up does Artemis perform Trans-Lunar Injection. Unlike Apollo, this path extends far beyond the Moon. This is a high-energy lunar flyby trajectory. The spacecraft swings around the Moon at a greater distance, testing deep space navigation and systems. The return path is longer, faster, and more demanding. When shown side by side, the evolution becomes clear. Apollo 11, efficient, direct, designed for landing. Apollo 13, the same path used for survival. Artemis 2, extended, flexible, and built for the future. All three paths return to Earth, but they carry different lessons. From reaching the Moon, to surviving space, to preparing for long-term exploration. The trajectories change, but the mission continues forward.
Here's a short narration of the return-to-Earth journeys. After completing their lunar objectives, each spacecraft began the long burn home, the Trans-Earth Injection, abbreviated TEI, a critical and well-timed engine firing that set them free from the Moon's gravity, especially for those missions that are captured by the Moon's gravity. This will free the spacecraft and aim them back toward Earth. I will now describe each of the return to Earth after TEI. Apollo 13 mission. Apollo 13 never landed, but its return was one of the most remarkable rescues in space history. After the explosion in service module oxygen tank, the Moon landing was aborted. The TEI burn, performed using the lunar module as a lifeboat, became the key moment that redirected the damaged spacecraft home. With limited power, cold conditions, and precise navigation, the crew looped around the Moon and began their fragile journey back, eventually re-entering Earth's atmosphere and splashing down safely. After the lunar landing by Apollo 11, Apollo 13 became the next most watched, tense moments and proved the grit of NASA. And then came the statement, failure is not an option. Apollo 11 mission. After Neil Armstrong and Buzz Aldrin left the lunar surface, Apollo 11's command module Columbia performed its TEI burn. From a distant lunar orbit, The engine fired once more, and the spacecraft slipped out of the moon's grip. The return journey was quiet but tense, 3 days of coasting through deep space before re-entry. As it hit Earth's atmosphere, the heat shield blazed like a star, and the crew splashed down safely in the Pacific, completing humanity's first moon landing mission. Artemis II mission. On its return phase after trans-Earth injection, Artemis II marked a new era of lunar travel. The crewed Orion spacecraft rounded the moon in a modern flyby profile, then executed a clean TEI burn to head home. Autonomous systems and upgraded life support made the journey smoother than earlier missions, but the essence remained the same: a precise burn, a long coast through deep space, and a blazing re-entry back to Earth. On April 11, 2026, the mission concluded successfully with a safe splashdown, signaling humanity's renewed reach beyond Earth orbit.
Once we understand orbital mechanics, traveling to the moon and back is no longer about constant effort in space. Instead, it becomes a journey guided mostly by physics, with carefully timed engine burns. The hardest parts are not the long travel in between, but the edges of the mission. First is the launch from Earth. This is the most powerful and dangerous phase. The spacecraft must fight Earth's strong gravity and thick atmosphere. Almost all the fuel is used just to reach space. If anything goes wrong here, there is very little time to react. Second is landing on the moon. There is no atmosphere to slow the spacecraft down, so everything depends on controlled engine firing. The spacecraft must slow down at exactly the right rate while also steering toward a safe landing spot. There is no margin for major error. Third is re-entry to Earth. The spacecraft returns at an extremely high speed. It hits the atmosphere like a blazing fireball. The heat is intense enough to destroy any weakness in the shield. The angle of entry must be perfect. Too steep and it burns up, too shallow, and it can skip back into space. When humans are on board, the risk becomes even greater. Life support must work perfectly, and there is no room for failure. Every system must be reliable because help is far away. So, while space travel may look routine in trajectory, it is actually a sequence of extremely precise and dangerous moments. The journey is simple in theory, but unforgiving in execution.